We present two-stream convolutional networks for dynamic texture synthesis. First, I'd like to thank my supervisors Marcus Brubaker and Derpanis from York University and Ryerson University. What is a texture? While a precise definition of texture remains to be found, most research consider it as visual patterns that exhibit local spatial variations while maintaining global homogeneity. If you were to take a small aperture and slide it across the texture, the contents should look roughly the same. Modern approaches of texture synthesis consists of an algorithm that takes in as input a target texture and white noise, and modifying the white noise until it matches the spatial statistics of the target texture. In other words, synthesizing an instance of the target texture. Our work builds off of Gaddis et al.'s model of texture synthesis using convolutional neural networks, particularly known for the invention of image style transfer and popularizing neural art. Before we discuss our approach, let's talk about how Gaddis et al. Implemented their algorithm. Gaddis et al. Started by taking an off-the-shelf network, BGG19, pre-trained on object recognition, and truncating the fully connected layers as well as the classification layer, with the intention to have a fully convolutional network encoded with the notion of natural imagery. As we know, convolutional layers output feature maps. By vectorizing these feature maps, then computing the inner product between these sets of vectors and their transpose, what results is a matrix that captures the correlations between features, the gram matrix or the gramian. In other words, the gram matrix indicates which pixels in these feature maps tend to activate together. And we can collapse this into a single gram layer. By computing the gramian at varying depths of the network, correlations at increasing scales are captured. In essence, this metric describes texture. After the initial forward pass, the gramian of the target texture is saved and set aside. Then the white noise is fed through the network and its gramian is computed. Finally, the task is to minimize the L2 loss between the white noise and the target's gramian. Gaddis et al. Coined this as the style loss, and it is also computed at other chosen layers across the network. Afterwards, we backpropagate through the network, and while keeping the weights of the network fixed, update the noise image. Over time, the network will have updated the noise image such that it closely matches the spatial statistics of the target texture. Due to stochasticity, the synthesized texture is not a copy of the target, but rather an instance of it. Now that we're done explaining static texture synthesis, let us talk about dynamic textures. A dynamic texture is like a static texture in the spatial sense, however, the requirement of homogeneity is extended across the temporal dimension as well. If you were to take that same aperture described earlier and slide it across the dynamic textures temporally, the dynamics between any pair of frames should be roughly the same. Dynamic texture synthesis is like static texture synthesis. However, instead of one image, you have several. Our approach to dynamic texture synthesis is a two-stream ConvNet that factors spatial appearances from spatial temporal dynamics, separately modeling the two. The appearance stream is tasked with modeling the per-frame textural information and is essentially Gaddis et al.'s model replicated across frames, with the sum of its style losses named as the appearance loss. The dynamic stream is tasked with modeling the dynamics between consecutive pairs of frames. We developed a compact ConvNet for optical flow prediction designed to be largely invariant to the appearances of the images, which should be characterized by the appearance stream. The sum of its style losses is known as the dynamics loss. The motivation behind the two-stream approach is that by factoring the appearance and dynamics of moving patterns and treating them independently, the overall generative process is simplified. This may lead to more realistic high-resolution images compared to a representation that does not distinguish between appearances and dynamics. Here are some of the results. In order to highlight the importance of the dynamic stream, we hold out the dynamic stream and synthesize dynamic textures only using the appearance stream. Over here we have a dynamic texture of a school of fish and the synthesized dynamic texture. By removing the dynamic stream, we lose temporal coherence. Although each frame matches the appearance of the target, the dynamics do not match. One of the limitations of synthesizing a limited number of frames is the obvious and jarring transition between the last and the first frames of the sequence. We treat the synthesized sequence as a circular loop with no explicit beginning and end. We extend the dynamics loss by including a dynamics loss between the last and first frames such that the last frame transitions to the first frame like a consecutive pair of frames. This results in what we call endless or infinite textures. An exciting aspect of the two-stream approach is that it enables us to have different targets for each stream. For example, on the appearance side, the target is a painting of fire, and on the dynamics side, the target is a video of a fireplace. With these two targets, the synthesized result is a painting of fire that moves like the fire in the fireplace. We call this dynamic style transfer. Here we have a painting of water and a video of water, resulting in a painting of water moving like the video of water. Here is the result painted onto the image the water painting was taken from. Lastly, we have a painting of a waterfall and a video of a waterfall, resulting in a dynamic texture that looks like the painting and behaves like the video. And again, here is the result pasted back onto the image the waterfall painting was taken from. There are many creative industry applications, including but not limited to computer-generated imagery, digital painting, and image editing. The ability to synthesize realistic dynamic textures would provide a new medium for communication, expression, and sharing of visual imagery, allowing users to transform the visual experience by bringing life to images.